this case methane or oxygen. Well, actually, oxygen double bond is specific to oxygen because there's nothing else that has an oxygen double bond. Apart from you, I suppose you could argue ozone, but that's confusing. So, but in general, they're not specific. They're not specific to these molecules, so they are averages. What's the other problem?
That fact that we take an average of the isotope. Is that
That's a good point. Yes, isotope does make a difference to bond energies because they're more massive, so the vibrations are different, so the bond energy is weaker. But you wouldn't be expected to say that. There's another key point though. You need to have. What's the definition of a bond energy?
energy required to break
Yeah.
It's the state.
The state.
Oh, right.
Gaseous state. Right.
Yeah, we can.
So the bond energy is the energy required to break 1 mole of bonds in the gaseous state. You need to be able to write that because that's one of the definitions you need to know. So I'll say it again. The bond energy is the average energy required to break 1 mole of bonds in the gaseous state. Note there are 3 points there. So I've seen that on a paper for 3 marks. The definition of bond energy for 3 marks. And what would the 3 marks be? The average, 1 mark, or the mean. So the average energy required to break 1 mole of bonds in the gaseous state, 3 marks. Right, that's that done. Now, what about the next thing? Well, the next thing is Born-Haber cycles. Now, Born-Haber cycles are easy peasy, but everyone thinks they're really hard. Well, they're not.
Difficult, they just take
Because
a long time.
all of Born-Haber cycles
I already got them.
is a big Hess's law diagram. And you already know, the fantastic thing about Born-Haber cycle is you only have to learn one to be able to do any of them. Okay, so all it is a big Hess's law triangle. So how do I make a Born-Haber cycle? Well, what I do is, first of all, I don't worry about drawing it as an energy level diagram to start with. What I do is I say, what is it that I'm trying to find? Well, I'm trying to find lattice energy. And the first thing I have to do is make sure I know what lattice energy is. So what's the definition for lattice energy?
And you're required to form a lattice from 1 mole of atoms in the gaseous state.
Close.
1 mole of
All of the lattice.
Yeah, 1 mole of the ionic lattice from its constituent ions in the gaseous state. So if we're taking sodium chloride, which is the easiest one, what we have to do is we have to form 1 mole of the ionic lattice. We're forming 1 mole of the ionic lattice. Okay, write this down if you don't know it. Lattice energy, 1 mole of the ionic lattice. The energy change when we form 1 mole of ionic lattice from its constituent ions in the gaseous state. Look, there they are. Constituent ions in the gaseous state. Now, as long as you know that definition, you can, and you know your other definitions, and to be honest, you've done a little bit of practice, you can easily do this, I promise. It's not difficult. Okay, people think it is, but it's not. Okay, so have confidence. I'll show you how to do it. What you do is you say, right, first of all, by the way, actually, one very important point. Around the world, different countries define this slightly differently. Some of them define it, in the UK we define it as the exothermic, i.e. the energy given out when the ions come together to form the lattice. So it will be a massively exothermic value, you know, minus several thousand kilojoules per mole, alright? But in the continent, in Europe, continental Europe, they normally define it as being breaking up the lattice. Now, do you know, it doesn't matter, but all I'm saying to you is watch out, because if you see a question in the IB, and I think the IB normally define it as the endothermic value, yes? So when you see a question in the IB and it says that the lattice energy is plus 3,246 kilojoules per mole, yeah? Then you know that that's the energy required to break up the lattice, and so the lattice energy is therefore this value going that way instead, okay? So it doesn't matter because the magnitude of the value is the key thing. And that's what you should always talk about, the magnitude of the value. So why does magnesium chloride have a higher lattice energy than sodium chloride? Why does it?
So why does magnesium have a higher lattice energy?
Why does magnesium chloride have a higher lattice energy than sodium chloride? Yeah, because the magnesium has a 2+ charge, and therefore it has a higher charge density. Okay, you've come across that term. Or it has a smaller ion. Okay, and so the attraction in the lattice is much greater because it's got a 2+ ion, and the chloride bit has remained constant. Okay, so we need to make sure you know that about lattice energies. So anyway, how do we get this? Well, what we do is we just take all our steps. What have we got to do to get from sodium chloride to sodium and chlorine ions in the gaseous state? Well, all we have to do is we look at all of our enthalpy changes that we've got on our piece of paper, and we do them step by step. So one of the first things we've got to do is we've got to get these into the gaseous state. We've also got to ionize them, but ionization energy, hang on a minute, that is defined as being in the gaseous state. The energy required to remove 1 electron from every atom in 1 mole of atoms in the gaseous state. You need to know that definition, it's on your sheet. Okay, so it's the ionization energy for sodium, but in order to get the ionization energy for sodium, we've got to make it into gaseous atoms. So let's first of all atomize delta H atomization. Now delta H atomization isn't going to work because what have we got to start with for delta H atomization? Elements. So somehow we've got to get to the elements. Now how are we going to do that? Formation, brilliant. So what we do is we say, look, that's the delta H formation of elements to sodium chloride. Well, let's actually put the elements in. Sodium, solid, standard state. Chlorine, oh, it's got to be Cl2, remember, because it's standard state. So we've got half Cl2 gas, because we've only got 1 mole of chlorine atoms there, so it's half Cl2 gas. What do we do next? Well, now we're almost there, aren't we? Because what we've got now got to do is we've got to atomize these. So if we do delta H atomization of sodium, then we get Na gas. And also, we can then do delta H atomization of chlorine gas, because although it's a gas, it's not atomized, so we've got half Cl2 gas. So what we then do is we atomize the chlorine. So now we've got Na gas, and then we've also got Cl gas, just a Cl gas atom. So we've atomized the sodium, we've atomized the chlorine. What are we going to do next? Ionize. Let's do delta H ionization energy for sodium, because what we do is we take away an electron, Na plus gas.
So is that Cl2 or should we see it?
Yeah.
That is not Cl2, that is supposed to be a bracket. Just Cl, because we've atomized it, it's no longer Cl2. And then, so we've got Na plus and Cl, but also in here we've actually got an electron now as well, because we've just ionized it, we've taken an electron away from sodium. And what we're going to do now, what are we going to do? The opposite of ionization energy is?
Electron affinity.
Electron affinity. So we need to electron affinitize chlorine. And look, we get to there. We've done it. So what we've done is we've successfully created our Born-Haber cycle just by going through all of those stages. Now, it's always the same. A Born-Haber cycle is not difficult because you learn one and you learn them all. What you have to do is, first of all, you have to put the delta H formation in, then you have to atomize the first element, then you have to atomize the second element, then you have to ionize the first element, then you have to electron affinitize the second element. The only thing you have to watch out for is if you've got something like magnesium chloride, because you have to do the first ionization energy of magnesium, then you have to do the second ionization energy of magnesium, and of course when you electron affinity, put the electron affinity value in for chlorine, you have to put 2 times the electron affinity value because you've got 2 atoms of chlorine to add an electron to. Everyone happy with that?
Which of those are exothermic and which are endothermic?
Well, it doesn't really matter because you're going to be given all of the values. Okay. Now, if very occasionally a question says, put that into an energy level diagram, then you can just do that. And just remember that all of the positive, you just put different levels in. Do you remember, like, right at the beginning I showed A and B and C, and I showed my arrows? All you have to do is put different levels in, and it doesn't have to be to scale, so it doesn't matter where you put them, as long as, if it's endothermic process, the arrow is going up, and if it's an exothermic process, the arrow is going down. So my advice would always be to do a Born-Haber cycle like that. And if the question doesn't specify, it doesn't say that it wants an energy level